In today's lecture, you will learn about Markov chain Monte Carlo method, which is commonly known as MCMC in abbreviation. And in this module, you will learn the Gibbs sampling, Metropolis-Hastings algorithm, and few other approaches to perform Bayesian computation. That means how to actually compute the posterior inference, in particular posterior mean, posterior standard deviation, credible regions, and so on, using Markov chain Monte Carlo method. Okay, in this lecture, we'll talk about Markov chain Monte Carlo method. And Markov chain Monte Carlo method recently became very popular because a lot of Bayesian calculation cannot be done without the simulation, in particular the Markov chain Monte Carlo or MCMC. In 1990s, it became very popular because before that, we used to do by numerical integration, which had limit that beyond 3 dimensions it was become much more complicated. So this actually created a big breakthrough in the field of Bayesian computation. So in MCMC, we'll talk about 3 major issues. First one is the Gibbs sampling, which we introduced a little bit before in the context of Bayesian linear model setup. And then we'll talk about Metropolis-Hastings algorithms. And finally, we'll talk about MCMC diagnostics. So let's start from MCMC. Suppose we have a joint posterior distribution P1 given P1 to P theta 1, say theta 1 is the parameter, up to theta k, given the data that we want to sample from. We can use the Gibbs sampler to sample from the target distribution if we know the full conditional posterior distribution for each parameter. For each parameter, the full conditional posterior distribution is the distribution of the parameter conditional on the known information and all the other parameters. And for this, actually, for the notations, you should go back to your notes. Now, there is one fundamental theorem called Hammersley-Clifford Theorem. It tells you that for 2 blocks, suppose we have a joint density f of x, y, comma, y, the theorem proves that we can write out the joint density in terms of the conditional densities f of x given y and f of y given x. So that means the joint density f of x comma y can be expressed in terms of conditional densities f of x given y and f of y given x. The theorem shows that knowledge of the conditional densities allows us to get the joint density. This works for more than 2 blocks of parameters. But how do we get out of the full conditionals? Now we'll talk about steps to calculating full conditional distributions. So we have a target posterior density. Then we calculate the full conditions for each. We consider full posterior ignoring constant of proportion or proportionality constant. We split the parameter vector into 2, say 1 and 2. Then consider a block of parameters, say 1, and ignore everything that does not depend on 1. Use the knowledge of distribution and what is the normalizing constant we ignore, and thus what is the full conditional distribution is obtained. We repeat the steps for other blocks. We generalize it for k blocks. So Gibbs sampler steps, let's talk about that. Suppose that we are interested in sampling from the posterior p of theta given y, where theta is a vector of three parameters, theta 3, 2, and theta 1. The steps to a Gibbs sampler are: pick a vector of starting values theta 0, defining a starting value some super pi 0 and drawing theta 0 from it. That's called initialization. Draw a value theta 1 superscript 1 from a full conditional of p theta 1 given theta 2 0, theta 3 0, and y. Draw a value theta 2 1 from the full conditional of theta 2 given theta 1, theta 3 0, and y. Note that we must use the updated value of theta 1 1. Then we draw a value theta 3 1 from the full conditional of p theta 3 given theta 1 1, theta 2 1, and y. Steps 2 to 4 are analogous to multiplying pi super 0 and p to get pi super 1 and then drawing theta 1 from pi 1. Draw theta 2 using theta 1 and continually using the most updated values. Repeat until we have m draws, with each draw being a vector theta t of values. Optimal burn-in and or thinning. Gibbs sample is a Markov chain with a bunch of draws of theta that are approximately from our posterior. There are various applications of Gibbs sampler which you learn in the notes, and there we talked about Poisson gamma problem and beta and binomial problem. Now we'll talk about another method where the complete conditionals are not in closed form, and therefore we have to use some special algorithm called Metropolis-Hastings Algorithm. So let's describe this algorithm. Suppose we have a posterior distribution p of theta given y, where as usual theta is the parameter and y is the observation. Then we want to sample from it, but the posterior does not look like any known distribution that we know. If the posterior consists of more than two parameters, then grid approximations is not possible. Some or all of the full conditionals do not follow known distributions. Therefore, Gibbs sampling is not possible for those whose full conditionals are not known. In such a case, we can use the Metropolis-Hastings algorithm. The Metropolis-Hastings algorithm follows the following steps. Step 1, we choose a starting value of theta 0, say. At iteration t, draw a candidate theta star from a proposal distribution q sub t of theta star given theta t minus 1. We compute the acceptance ratio, and the formula is given in the notes, which is basically a ratio of function p evaluated at theta star given the y and divided by q sub t theta star given theta t minus 1, that is the previous stage. Whole thing divided by p of theta super t minus 1 given y divided by q of t theta t minus 1 given theta star. Then we accept theta t equal to theta star if u is less than the minimum of 1 and r, where u is uniform 0, 1. Otherwise, we don't move, that is theta t equals theta t minus 1. we repeat the steps 2 through 4 m times to get m draws from P of theta given y with optional burn-in and or thinning. Note that theta super 0 must have positive probability, that is, probability density evaluated at theta 0 given the data y should be positive. Then we draw theta star from q sub t theta star given theta t minus 1. The proposal distribution determines where it moves in the next iteration of the Markov chain. The proposal distribution is analogous to transition kernel. The support of proposal density must contain the support of the posterior. If a symmetric proposal distribution is considered that is dependent on theta t minus 1, then it is known as random walk Metropolis sampling. In step 2, the proposal distribution does not depend on theta t minus 1. Then qt of theta star given theta t minus 1 will be qt of theta star. Then it is known as independent Metropolis-Hastings sampling. In this case, all candidate draws theta star are drawn from the same distribution regardless of where the previous draw was. This can be very efficient or very inefficient depending how close the proposal density with respect to the posterior density. Typically, if proposal density has heavier tails than the posterior, then the chain will behave nicely. So this is very important to choose the proposal density, that it should have heavier tail than the posterior distribution. So that means this should form an envelope function. The computational acceptance ratio is very important. In this case, where our proposal density is symmetric, then R has a simpler form. If the candidate sample has higher probability than the current sample, then the candidate is better, so we definitely accept it. Otherwise, the candidate is accepted according to the ratio of the probabilities of the candidate and current samples. Since R is a ratio, we only need to know the posterior distribution theta given y up to a constant. That means evaluation of the normalizing constant is not needed. We decide whether to accept theta star. These are the important points. We accept theta star as theta super t with probability minimum of r and 1. For each theta star, draw a value u from the uniform 0, 1 distribution. If u less than equal to r, we accept theta star as theta super t, otherwise theta super t minus 1 equals theta t. Candidate sample with higher density than the current samples are always accepted. Unlike in rejection sampling, each iteration always produces a sample either theta super star or theta super t minus 1. Now we'll talk about some fine points regarding the acceptance rate. It is very important to monitor the acceptance rate, the fraction of candidate samples that are accepted of your Metropolis-Hastings algorithm. If acceptance rate is too high, the chain is probably not mixing well. That is, the chain is not moving around the parameter space quickly enough. If the acceptance rate is too low, your algorithm is too inefficient. that is rejecting too many candidate samples. What is too high and too low depends on the specific algorithm, but generally random walk somewhere between 0.25 and 0.50 is recommended for the acceptance rate. The independent scenario, something close to 1, is preferred. So in this module, you have learned how to use MCMC or Markov chain Monte Carlo method to compute posterior inference, that means a Bayesian inference.